Come on in, everyone. Feel free to ask me any questions if you have any before we start. No questions? I have the chat box open too if you want to post it that way. But got a couple minutes before class starts, maybe two. Another one. Still a minute left if anybody has any questions. All right. Looks like no one has any questions. Looks like we got about 8 of us in class. It's a small number, but better than nothing. I guess we should go ahead and get started. When I left you last time, I started off with giving you an idea about equation that I use when I'm doing conservation of energy. This first chapter that we're actually looking at, though, is actually not a chapter on conservation of energy. It's basically a chapter called work and energy. So it's trying to get started where you can learn what work and energy are. I'm just looking back at the notes real quick. Where was that? No, not that one. Oh, there it is. So yeah, the last thing I did was ended up showing you the potential energy initial plus kinetic energy initial plus work in is equal to potential energy final plus work final, or excuse me, plus kinetic energy final plus E loss plus work out. Okay. So I need to show you where all that came from, and that's mostly what we're going to work on today. And then when we start into chapter 8, which we'll start next time, we'll make more sense of that stuff. So again, since I now have about 14 people in here, does anyone have any questions before we get cracking? All right. Looks like no one's typed anything and definitely no one said anything. So let me get started with talking to you about work. So if you imagine maybe you're mowing a lawn. What I'm trying to convince you is that this idea of work that we use for physics is somewhat related to what you might think work as. So for instance, I know most of you would call mowing the grass work, and in that sense, I'm going to exploit that process. So imagine a yard that's say 90 foot wide, and you're using a 2 foot wide lawnmower. Uh, let's say you like your yard nice and neat, so you want all your rows to be one particular direction. So you run parallel to say the eastern border of your lot, and that takes up 2 feet. And then you run backwards, that takes up another 2 feet. Now you're 4 feet, and then you go another 2 feet cut out, and then another back. So now we're back up to 8 feet. And you keep on doing that. And basically you make 45 trips. And maybe the yard is, let's say, 100 foot deep. So it's 90 foot wide, 100 foot back. So you're walking 100 foot and then turning around, pushing your mower over 2 feet, going back over the other way, walking 2 foot over, going back the other way. So you're doing 2 foot wide swaths at 100 feet times 45 times. So it's basically 4,500 feet. Now, if I told you that you wanted to do that, or I asked you, would you prefer to do one that's 90 feet wide by 200 feet wide, deep? I think you'd all agree that the 200-foot deep one would be twice as much work, at least, as the 100-foot one. And in that sense, you come up with the idea that work is directly proportional to a distance traveled, because clearly you're traveling, in the first case, just a 100-foot walk, turn around, 100-foot back, 100-foot walk, turn around, 100-foot back. In this second case, where you're talking about a 200-foot deep yard, then you're going 200 feet, turn around, 200 feet back, so on and so forth. So that ends up becoming quite a few more feet. So yeah, work and force should be thumbs up, thumbs up. And of course, you would want to do some experiments, or you want to correctly define work in such a way that it has certain parameters. And what we found is the way that the work works the best is when the work is directly proportional to the force applied, or excuse me, in this case, directly proportional to the distance that's traveled. So it's not distance squared, it's not distance to the 1/2 power, but it is definitely 1-to-1, up and down, up and up. So thumbs up, thumbs up. So that's one thing. Now if you imagine taking the lawnmower and let's say you only are going to cut the 90 feet by 100-foot yard, and that's the only one you're going to cut. But you have a choice of 2 mowers. One mower is extremely light. It's been designed to be ergonomically helpful and that sort of thing. So you really can push with a minimal amount of force. It's got a really powerful engine. It's not going to slow down. It's got really sharp blades. It's going to cut every blade. And even if the grass gets really high, the engine's so high powered, they'll just cut right through. Right. Well, with all that in mind, then you're focusing on how much force you have to apply to the mower. And since this mower is ultra light and ultra efficient and ultra ergonomic, the force you're actually going to apply in mowing that lawn is quite a bit less than the force you're going to apply with the regular mower, or with a god awful mower. For instance, you might actually have the type of mower where for starters, the axle was kind of rusty, but basically you propelling the wheels is what turns the blade directly. And maybe it's a ratio of 2 or 3 turns to 1 or something like that. But still, even if they're really sharp, they're not going to be sharp for very long. It's going to take a lot more work. You're going to have to push harder. So in that sense, I think you'd also agree that the more cumbersome and more heavy mower would be more work. So in that sense, you come up with not only is work and force thumbs up, or excuse me, not only is work and distance thumbs up, but now you're getting work and force is thumbs up. And that's really where we land. Now, we in the physics world, when we're trying to think of something like work here, we really don't want to count any components of force that aren't helping us. So for instance, if I am pushing if I'm pushing on a box in such a way that I'm pushing down and to the right, really my only goal is to push to push the box on the floor to the right. So the component of force in the downward direction is not helping me. So why would I count that? Well, that brings us to the next part, which is we really only want the component of force that's parallel to the path traveled. And to do that, there's a trick that we use from mathematics, from vector algebra and vector calculus, called the dot product. The dot product is, and I'll show you 2 ways of calculating it, but basically if you take 2 vectors, A and B, and you put them tail to tail, say, like this, say, and the tail is down here where my fingers are meet my hand. Now, if you take the dot product of them, you end up getting the magnitude of A times the magnitude of B times the cosine of this angle right here between them. And that's the dot product. That's one of the ways you can calculate the dot product. The other way you can calculate the dot product is you can take the x component of A and multiply it by the x component of b. Take the x component of b, or excuse me, the y component of a, and multiply it by the y component of b. And then finally take the z component of a and multiply it by the z component of b. And then add those three those three products together. Notice there are scalar now. That's another name for the dot product. It's called the scalar product. But you have three products, ax times bx, ay times by, az times bz, and you add those together, and that gives you the dot product as well. So there's two ways you can calculate it. I'll write these formulas in a second. But it turns out we're going to use that, and we're going to use that over and over again. So whenever we want to pick off a component of a vector that and we want the component of the vector that's parallel to another vector, then we're going to use a dot product. And there's even a operation called projection, like the projection of vector b on vector a has a very specific value in the vector algebra world, and you can make that up. In fact, I make it up every time I try to discuss it because I don't memorize those formulas, but I understand the way it works, so I can come up with a formula really quickly. So that's something that's helpful. Another thing we'll learn later is something called the cross product, and also called the vector product of two vectors. And that one's really odd in that it gives you, in some sense, perpendicular components. So if you ever need to know the component of a vector perpendicular to another vector, then the cross product is what you're thinking. And that one actually gives a vector product out. And it turns out that if you have vectors A and B again like this, well, if you complete the parallelogram for this, so you have this and this making a parallelogram, it turns out that not only does A cross B give you something relating to the component of A parallel to B, or the component of B, or excuse me, perpendicular to B. So not only does the cross product give you a component of A perpendicular to B, but it also gives you a component of B perpendicular to A. Or you can just take the cross product all by itself, and it actually gives you the area of that parallelogram. So that's something else we'll use. So it turns out we now have two really cool tools just by me discussing them, the cross product and the dot product. And the dot product can be used to find the component of the vector A that happens to be parallel to vector B. And you get that by doing A dot B. And the vector component of A perpendicular to B can be found by taking A cross B. Okay, so let's get started from that standpoint, and I'm going to go ahead and generalize what the work is. So I've made the argument that work is consistent with our definition of work, in that we think the more work you, or the more force you apply in doing a job, the more work it is. That's consistent. The more distance you travel, that seems to be more work as well. You might have said time would be a relevant parameter, and that could have been, only I was going for a very specific one that we happen to know works out and gives us a lot of meaningful stuff. So I stuck to the idea of what the definition is. So if you happen to want to calculate work, what we found out is it's proportional to F, and I'll put the little parallel symbol there. Oh, and you're not looking at this because I have not shared my screen yet. Look, I figured it out all by myself. I'm very big. I'm grown up. I'm a teacher now. Sorry about that, folks. All right, here we go. So I'm writing W is the symbol we use for work. And I told you that it's work, W-O-R-K. And you'll see in a second, it's supposed to be approximately F parallel times D. So the F parallel means the component of the force parallel to the distance vector. So you can imagine a distance or a displacement vector that points from the point at which the object you were pushing was at when you first started pushing it, to the point at which the object was at when you finished pushing it. So that would be your displacement vector. And if you take the force of F, that's the component of it that's parallel to D, you would get the work. But what happens if that doesn't work out? Like, what happens, for instance, if as you're walking along the path, along the displacement vector, what happens as the force changes? Well, that takes more. You're going to have to cut up the path in small pieces and then evaluate the force in each of those small pieces. And if the pieces are so small that the force is basically a constant and the separation angle between the force and the path is a constant over that whole period, then you've done good. But if you haven't, you have to go even finer to smaller details. So one way we can do this, for starters, at least getting the F parallel D part, is we can say work is directly related. Actually, I'm not going to say directly related anymore. I'm going to say approximately equal to, because it's not, this one isn't considering the case where I'm talking about the force could vary. So in this case, you'd say F dot D vector, where again, the D vector is the displacement vector. And that, of course, is the magnitude of F, which we can write as F without the vector symbol, the magnitude of D, which we can write as D without the vector symbol, and then times cosine theta. And in that case, what we're talking about is, this is the force F, for instance. This is the displacement D. They're tail to tail, so this angle right here is theta. And you'll notice if you were to draw a perpendicular to D like this, then that makes a right triangle. And this component right here is F times cosine theta. So this is in fact F parallel. Now, alternatively, we could have done something like this. So I just want to show you that no matter which one you do, it's always going to work. So we could have taken a vector perpendicular to F, let's say like this, and then this would be perpendicular. And in that case, again, the angle is theta, but notice they're still tail to tail. But now the vector, let's try yet another color. I'm going to say this color. But now this right here is the vector D cosine theta, which is D parallel. So we could write that as F parallel to D, or we could write D parallel to F. Doesn't matter. But this F D cosine theta, and therefore the dot product, really is all we need to pick out the components that are parallel and stuff like that. So I'll tell you from the start, what the actual formulas are. So A dot B is equal to the magnitude of A, which you can write with absolute value bars and the vector symbol, the magnitude of B times the cosine of the angle between them. Again, you're going on the assumption that A and B are tail to tail, and then this is the smaller of the two angles that separates them. Now, there's another version that you can use, and that's what I was telling you a second ago. It's AX times BX plus AY times BY plus AZ times BZ. So this comes in handy, for instance, if you actually know, let's say, for instance, I'm going to draw a coordinate system and give you some idea of what we're talking about here. So in solid state physics, one of the things you cover, at least initially, is the lattice in which atoms combine to make a pure element as a solid. So for instance, you might call this the x-axis, this one the y-axis, and this one the z-axis. But you could, for instance, have an atom here, and then an atom here, and then an atom here. And now I got to go one more atom over here. And then up here, I'd have an atom. And right here, I'd have an atom. And right here, I'd have an atom. And right here, I'd have an atom. So these are all individual atoms of different planes. So for instance, the front plane has these front four atoms right here. And then there's a side plane that has the left four atoms. There's a right side plane that has the right four atoms, so on and so forth. But in order for you to understand how these atoms interact as atoms, you have to use quantum mechanics. And one things we've learned is the angle of the bond between two adjacent particles, for instance, really matters. So this is basically called a cubic lattice. But there's also a face-centered cubic. So you could, for instance, have another atom in the face of this one, another in the face of this one, another in the face of this one, another in the face of this one, then a face on one on the face on the top, and then one on the face on the bottom. Now that is a face centered lattice. Okay. But you could also have, for instance, I'm going to draw a whole new one here. Let's say you could have, for instance, this guy, this guy, this guy, this guy, and then this guy, this guy, this guy, and this guy. And I'm going to say sort of the cube that we're making is this, so that you can see the three-dimensionality of it. But now inside of there, we could have, for instance, a single atom in the center. And that would be connected to this guy by that little bond there, and to this guy by that little bond there. Okay. Well, you might not know exactly what the angle is here between this bond and let's say this bond back here. So there's a bond between those two, this guy's up in front, between those back atoms and this middle atom. And if you wanted to find that, that might be kind of complicated, but let me show you what you can do with this. If, for instance, you actually had it in a coordinate system, then you know this point right here is 0, 0, 0. You know this point right here is, let's say 0, A, and then 0. So we're basically treating this cube, if you will, as if it's a cube of length A. So this is A, this is A, and this is A. So I can easily get the vector there. So oops. I can easily get the vector pointing from that back left to that back right corner. Dang it, I did the same thing again. So V from back left bottom to back right bottom is simply let's, and I'm saying V like the vector, so let's say that's vector A, and it's going to be 0 minus 0 for the I hat component. Remember, we can use these less than and greater than symbols to indicate vectors. And then it's going to be A minus 0 for the J hat component. And then it's going to be 0 minus 0 for the K hat component. So basically, we just get A J hat for that vector. Okay. Now I want the vector that points from that back right corner to that center atom. So back right bottom to body centered atom. So in this case, it's a body-centered cubic is what this is called. So I think you can see that this vector, let's call it B, and I'm going to do it in red. This vector B is going to be, now the center atom will have x equal a over 2, y equals a over 2, and z equals a over 2. So it's going to be a over 2 minus 0, a over 2 minus 0, and a over 2 minus 0, which gives me a over 2 I hat plus a over 2 j hat plus a over 2 k hat. So now I can take a dot b and call it basically 0 times a over 2 plus a times a over 2 plus 0 times a over 2. And in that case, I get a squared over 2. I think you can tell that the magnitude of A, which is also just called A, that's going to be just plain A. And I think you can probably tell that the magnitude of B is going to be the square root of A over 2 squared plus A over 2 squared plus A over 2 squared, which is going to be basically the square root of 3 times A over 2. So we can also say that A dot B is equal to A squared over 2, but it also equals A times the square root of 3 A over 2 times the cosine of the angle between them, which tells us that theta is equal to the cosine inverse of, now you can see here that basically this a over 2 is going to cancel out with this a over 2, and this a is going to cancel out with this a. So I'm just going to get cosine theta of 1 over the square root of 3. And that will give me the actual angle. And if I do that, I'll say second function cosine inverse 1 divided by the square root of 3. And that gives me 54.73. Oops. 0.73 degrees. So that's the angle between that green bond and that red bond. Anybody have any questions on that? Now, this dot product is something, like I said, we'll be repeatedly using it. We'll use it, for instance, every time we want to calculate work, because work needs a component of force parallel to the displacement. But anytime we need other quantities, like later we're going to learn something about magnetic flux, we're going to learn about electric flux. And in those cases, you want to know the component of, let's say, the electric field or the magnetic field that happens to be exactly perpendicular to, let's say, the window it's going through. So we represent a window's area by a vector that's perpendicular to the window and whose length is exactly equal to the area of the window. So if you dot product the electric field with that vector, then you're only going to get the component of the electric field that's perpendicular to the window. So that's another time we can use it. So let me just reiterate what we've got here is we've learned a formula, A dot B equals A times B times cosine of the angle between them when they're tail to tail, but it also equals AX BX plus AY BY plus AZ BZ. I will accompany that with a drawing of A and a drawing of B and the angle theta. And I will tell you it's technically a linear operator too. And I'll say A dot B equals the dot product of A and B, but it's also called the scalar product, because I've seen students over and over do this, so make sure you don't. When you take a dot product, you actually take two vectors. It's like a machine. It's an operation or an operator or something like that. It's a machine that sucks in two vectors and spits out a single scalar, as compared to, for instance, the cross product, which takes in two vectors and spits out a vector. So that's something you can learn about the scalar product. Here's something else that's kind of neat is I've never been one to use the law of cosines until I figured out how I could derive the law of cosines using dot product. So let me show you that really neatly. Let's imagine, for instance, that you have a vector A right here. And this time I'm going to put the vector head to tail like this, and this will be the vector B. Okay. I think you can see that, in fact, the vector from here to here is the vector A plus B. I think you can also see that if A and B were tail to tail, then this angle right here would be the theta that we use for the dot product. So I can say that A plus B is equal to, let's define it to be C. And now what I'm going to do is I'm going to take the dot product of A plus B with itself. So A plus B dotted with A plus B equals C dot C. So this is for starters, this is a linear operator. That's something that we're going to come back to over and over, but it also just behaves like other things. So the FOIL method is necessary. So I do A dot A for when the first term hits the first term. And then I do A dot B. I tell you that, at least in the form that we're currently using it, the dot product allows multiplication to be reversed with any change. So B dot A is also A dot B. So the next term is A dot B again. Again, I'm telling you that A dot B is the same thing as B dot A, at least in this context. And then finally, we got B dot B like that. On the other side, we got C dot C. Well, I think you know that if you took a vector, let's say A X I hat plus A Y J hat plus A Z K hat, and you dotted it with the same vector, you would get ax squared plus ay squared plus az squared, which I think you recognize as a squared, right? The only difference is with the Pythagorean theorem, you need to take the square root to get the magnitude. So instead of taking the square root, I just left it as a squared. So now I can write this whole expression as a squared plus b squared. So that takes care of this term. Well, let me do that with a different color. That takes care of this term, and that takes care of this term. Now I'm going to say plus 2 times a times b times cosine theta. And all that Notice I've now taken care of this term, and all that's equal to c squared. Oops, didn't want to do it in that color. All that's equal to c squared. Now, I think you can see from this that this is the law of cosines, basically. And when I saw that, it was like I never had to worry about exactly where the angle was, whether the sine between the a squareds and b squareds and the 2ab was positive or negative. I just knew the formula was right and I could use it. So that's one of the advantages of having it. Another advantage, of course, of having the dot product is the dot product is, as I told you, it's a linear operator. And when I use a word like operator, it means you're sort of thinking of it as being a thing by itself, and you're going to put something next to it. And that's what you do. This is a two-input operator, the operator being the dot product, and it takes two vectors. So let me show you what I mean by it being a linear operator. If you took A and dotted it with B, you could write this as AX, and I'm just going to do two components. The Z would just be an extra term, but it'll save me a little bit of paper and time. So I'm going to say this is just AX I hat plus AY J hat. That's the whole vector. I'm going to dot that with BX I hat plus BY J hat. Now, this is where I'm just going to use your familiarity with the process of multiplication of polynomials and just let you know that the dot product behaves the same way. So what's going to happen is this first term, the AX and the BX term, are going to multiply, and I'll get oops, let me go back to writing in black. I get AX I hat dotted with BX I hat. And now I've got to have the first term hit the second term. So this one's going to be plus AX I hat dotted with BY J hat. Now I got to make the second term of the first fraction of the first factor hit the first term of the second factor. So this is going to be plus AY J hat dotted with BX I hat. And now I've got to make the second term hit the second term. So in this case, it's going to be plus AY J hat plus BY J hat. Of course, you just had basically some more terms if it would have been a AZ K hat and a BZ K hat. Now I'm going to show you the linearity part. So it turns out that you can let scalars pass right through dot product. So like this BX that's between the dot and the I can just change this to AX BX I hat dot I hat. That's one of the properties of linearity, is you can take a scalar times a vector, and the scalar just comes out in front of the dot product, and you can just do the dot product on the vector parts. The same thing happens with the next term, which would be AX BY I hat dot J hat plus AY BX J hat dot I hat plus AY BY J hat dot J hat. Now remember the formulas for the dot product. It's the product of the magnitudes of the vectors and the cosine of the angle between them. So can someone tell me what the magnitude of I hat is?
One.
Exactly. And it's one exactly. It's not 1 newtons, not 1 meter, not 1 kilometer or anything. It's just plain one. So thank you for that. And then the other one, of course, has the 1. And then what's the angle between I hat and I hat?
Zero.
0. So you take the cosine of 0 degrees, which I could have written with the same color. Of course, the cosine of 0 is 1. So we just get 1 there. What do you think we're going to get when we do I hat dot j hat? Anybody? I hat, remember, has a magnitude of 1. J hat has a magnitude of 1. But what's the angle between I hat and J hat? I think what I heard someone answer, they might be misremembering dot product versus cross product, but the angle between them is 90. So the cosine of 90 degrees is 0. So I get 0 for that one. I get 0 for this one. And for j hat dot j hat, I get 1 again. And that's exactly why the formula that we had, the formula that we had is correct. It's ax bx plus ay by. Now, if we'd had the z, it would come out plus az bz. But the main thing is I'm showing you that by carrying out the multiplication, we can actually do the individual dot products on the individual I hats, j hats, and k hats, and you'll get exactly the same formula. So that comes in handy. In general, what the rule that it's a linear operator means is that you can take A and dot it with, let's say, A1, or let's not say A1. Let's say I'm going to dot it with B1 times B vector plus C1 times C vector. And this will just become B1 times A dot B plus C1 times A dot C. So that's linearity that I'm talking about here. Any questions on that? We're going to use that over and over again, especially in the 242 course. Any questions on that? So now that we have it, it looks like we don't have any questions. So now that we have it, I'm in a position where I can go ahead and make use of what argument we made about the work. So what we're going to actually define work as is work is equal to the integral of f dot dl. This is called a line or path integral. Okay, that's a term from vector calculus. And unless you go to a pretty good sized school, you're probably never going to have a course in vector calculus. I think when I went to East Carolina, they have a pretty decent size, though it's not that super strong. They have a decent sized math department. And they offered, when I was there, they offered vector calculus about once every 2 years. I don't even know that they offered anymore. I did not find an undergraduate class like it at Chapel Hill, which surprised me. So I might just be wrong on that one. But generally speaking, vector calculus is not something that's easy to come by. Differential geometry and tensor calculus and calculus on manifolds, those are also fairly esoteric courses that you also might not get. But we're going to be doing all that stuff in this course. What I need you to know about a line or a path integral is a couple things. One, the integrand has to be evaluated on the path or line that you're traveling along. Okay. This is true too. There's another type of integral we'll learn later called a surface integral, where you're integrating on a surface. And what you have to do is take the individual f, which might be a function of x, y, and z, And if you've got, for instance, for a particular path, if you've got a constant x value or a constant y value or a constant z value, or maybe two or more of those, then you've got to set the x to that constant value, the y to that constant value, the z to that constant value. And you might even have to do something similar with the dx, depending on how you define the dx. So that's one part. The other part is you must use either DL or the range of integration to indicate, the direction in which you are integrating. The other will be in the increasing coordinate direction. Now, this is the tricky part. I say tricky part. It's actually the part that makes you get it right more times than you really warrant getting it right. It's been my experience. So you're either going to use the range of integration, like if you're integrating from x equals 0 to x equals 5, you can indicate that by integrating from x equals 0 to x equals 5, and then you just put DL in the positive x direction. Well, in that case, that happened to be the same direction you were going, so it looks like you're actually using both ways to indicate the direction. That's not the case. That just happened to work out that way. If you happen to be integrating from x equals 5 to x equals 0, then you either put DL is equal to negative dxi hat and you integrate from 0 to 5, or you integrate from 5 to 0 and you put DL as dxi hat. That's what I mean. So, for instance, if you imagine, let's say, example, let's say f is equal to 2x I hat plus 2y, let's say, no, let's do 3y j hat. And let's say we're going to integrate. Here's my x-axis, here's my y-axis. And let's say I'm going to go from this point right here. That's 1, 2, 3, 4. 1, 2, 3. Let's say I'm going to go from 4, 3. That's point A. I'm going to go this way. And then I'm going to integrate this way and end up at this point by going through this point. So point B is going to be y equals 0, but x is still 4. And then point C would be 0, 0. Okay. So if I wanted to calculate the work in that case, I would say work is equal to the integral of f dot dl, which I'm going to say is equal to the integral from A to B plus the integral from B to C. And now I'm going to evaluate that. So as I'm doing A to B, notice that is the path x equals 4. and this is the path y equals 0. So with the path of x equals 4, oops, need to go back to red. With the path of x equals 4, the f being 2x plus 2xi plus 3yj gives me 2 times 4 times I hat. That's what I mean by you have to evaluate the integrand on the path plus 3yj hat, and that's going to be dotted. Notice I'm going to use, in this case, I'm going to use the range of integration to designate my direction. So I'm going to say I'm integrating from y equals 3 to y equals 0. Okay. And then this guy just has to be in the positive y direction. So I'm going to say it is dy j hat. So indicates direction. And this is in positive coordinate direction. Okay. And then I have to do the other integral, which is plus the integral of, now in this case, the y is actually 0 and the x is going to range. So I'm going to say 2x I hat plus 0j hat. Now this one, I will use the dl to indicate the direction. So I'm going to say negative dx I hat. And by doing so, I've actually got to choose the positive coordinate direction, which would be from x equals 0 to 4. Okay. So I'll say indicates direction. Okay. So hopefully that is enough notes for you to understand it. Now, what we end up having here is when I do the dot product of 8 plus 8 I hat plus 3yj hat dotted with dyj hat, I just get the integral of 3y, oops, that looks really bad, of 3y dy from 3 to 0. That's the first integral. Plus, in this case, only the x1 survives. So I get the integral from 0 to 4 of, let's say, a negative. So I'm going to go ahead and make this minus or this plus into a minus. And that minus came from the negative sign in there. Okay. So now this is going to be 2x dx, and of course the I hat dot I hat was just 1, and the j hat dot j hat was just 1 in the previous integral. So what I'm going to get now is the integral of 3y is 3 halves y squared from 3 to 0 minus, now this one's going to become 2 halves x squared from 0 to 4. So 3 halves times 0 minus 9 minus 2 over 2 is just 1. So this is going to become 16 minus 0. So I get negative 27 over 2 for the first integral. And for the second integral, I get negative 16. So I could make that 32 seconds. So it'd be negative 27 over 2 plus negative 32 over 2. That would be negative 59 over 2. And work is actually measured in joules, where I'm saying the unit of work is equal to the unit of force times the unit of distance, which equals a Newton meter, which is defined to be the joule. Okay. So hopefully that explains a little bit about how the path integral, line integral stuff goes. Anybody have any questions about that? All right, so let's go on now and make some use of this. So we see in simple cases, like if I'm, let's say if I'm pulling a box like this across the surface, and let's say I'm pulling it with a force of 50.0 newtons at an angle. Well, let's not be too original. Let's use one of our 3, 4, 5 triangles, because that's really cool, right? Let's say that's 53.1 degrees. Okay. Now work is equal to the integral of F dot dl is the general rule. But in this case, notice the force is not changing. And the relative direction between the force and the dx is not changing either. And I'm going to say this thing's going to go at distance d equals 100.0 meters. Like that. Okay. So in this case, it actually becomes quite simple. The work is just going to be equal to, let's write solution here. The work is just going to be equal to 50.0 newtons times cosine 53.1 degrees times 100.0 meters. So if I take the cosine of 53.1, obviously I'm going to get 0.6. I multiply that by 50, and then multiply that by 100, I get 3,000. Whoa, Nelly. I get 3,000 newtons times meters, which equals 3,000 joules. So I shouldn't say most of the time, but a lot of the time you can just take and multiply the force. In fact, if you're lucky enough for the force to be parallel to the actual displacement, you don't even need the cosine function. Then it's just force times distance. But that's a typical thing. For instance, if you are talking about the friction force that a tire applies to the ground just before a car gets in a wreck, say, and this is actually what police officers are doing when they're out there with the trundle wheels measuring skid marks, is they're using that to determine, using the work energy theorem, to determine how fast the car was going ahead of time. So I'll show you that equation as well. But that's a simple case because the friction force is just mu kinetic. Since it's skidding, it's mu kinetic instead of static, but it's mu kinetic times the weight. Unless the car is on an incline, then it'd be, mg cosine theta. But in this case, it's mg times mu. That's the force. And it happens to be exactly anti-parallel to the direction that it's going. So you end up taking the cosine of 180, which is -1. So you just get negative mu static mg times d. And that's it. That's the whole work done by a car skidding a distance d. If the coefficient of static friction is mu s and the weight of the mass of the car is m. Any questions on that? All right, so let's look at another instance. In this case, we're going to look at an instance where I'm going to use it to derive something called potential energy. Potential energy is a energy an object has as a result of its position. So for instance, if you have a turtle sitting on the ground, there's very little chance that a turtle could just use his body weight to drive a nail. And that's sort of my go-to example of what has energy. Anything that has the ability to drive a nail has energy. Now, this nail can be really, really, really thin, like, a micrometer in diameter, and it can be really, really short, like a centimeter in length. And it can be driven into something really, really soft, like hot butter. Okay. That's sort of the extremes you imagine. And yes, a turtle standing up on his little legs could actually use his weight to squish such a small nail into some hot butter, in which case the height he had above the ground was enough to give him the potential energy for him to drive the nail. But let's imagine another scenario where I have an actual mass and I'm going to have it sitting on the ground, and then I'm going to lift it up to some height and find out how much work I did. Now, the work I put into that will be called the change in potential energy. So we're going to say, let the change in gravitational potential energy which I'm going to write as delta U because it's change in. Let the change in gravitational potential energy, delta U, be defined as the work required to lift the object from y equals 0 to y equals h. Now, when I do this, I don't want to put too much force into it. I want to put just enough force to where it's free to move, but doesn't actually speed up, because if it's sped up, then I'm giving it another kind of energy called kinetic energy, and we're trying to avoid that. So what I'm doing is imagining taking some object of mass m and putting it in equilibrium with a force going up, and just waiting so long that eventually a molecule or a gnat or something will fly by and knock the mass up just a little bit. And then I'll keep holding that force, and it'll happen again. I'll keep doing it until it eventually gets to the height h. And when I've got to the height h, then I will know what the total potential energy is. Specifically, the change in potential energy will be equal to the work done. So now if I look at that, you can say, okay, well, here's my x-axis, here's my y-axis, the object's going from here to here, and this height is h. Okay, the free body diagram for this shows that I have a positive y-axis that way, and the force I'm going to be applying to it is going to be that direction. And then the force that gravity is applying to it is mg. And of course, its mass is m. So I want the summation of the forces in the y direction to equal mass times acceleration in the y direction. But I want this acceleration in the y direction to be 0 because I don't want to do so much work that I actually make it go fast. I don't want it to speed up. So to do that, I'm going to make it an equilibrium situation. That's going to give me that F minus mg is equal to 0. So F is just equal to mg. So now I can say, let's do it in blue, delta U, which is U final minus U initial, which are normally written U sub F minus U sub I, is equal to the integral of, now my force is the force that I'm applying to the object. So that's the work I'm putting into the system. And that points in the upward direction, but it clearly has a magnitude of mg. So I'm going to say it's mg in the j hat direction. So that's my force. And in this case, it's actually not going to change. I didn't actually technically have to do an integral here, but later you'll see when I do a spring, it will have to use an integral, and it's best to know how. So now that I do this, I'm going to say, okay, I will let my range of integration dictate or explain what direction I'm going. So I'm just going to put my dl in the positive y direction. So I'm going to say this is dy j hat, and I'm using the fact that it goes from y equals 0 to h to indicate direction. But again, in this case, it's like the other one. It's sort of trivial in that both of them are pointing in the positive direction. So I would have got the right answer, not even thinking about it. All right. Well, when you take the dot product of mg j hat with dy j hat, you basically just get mg dy times j hat dot j hat, which is just 1. So I'm going to get m times g times the integral of dy from 0 to h, which gives me m times g times h. Now, what that means, and this is the right answer, by the way, I will go ahead and box it off. I'm going to say delta U equals U final minus U initial is equal to MGH minus 0. And that's because I want you to understand that the reason that I only have one term is because the H being 0 was what caused the mg times H for the first term or the second term in the subtraction to be 0. So, and by the way, it doesn't matter where you call your 0 of coordinates, because ultimately it turns out that the change in potential energy is usually way more important than the actual potential energy. So we now have a formula in general, potential energy, and there's other types, by the way, so I'll put potential energy gravitational. And this is grav near Earth's surface is equal to m times g times y. And again, as I told you, that is for any origin, it's m times g times y. And as long as you stick with that origin, everything will work out. So now we've used this to determine the potential energy due to gravity near the Earth's surface. Because if you actually go when you're so far away from this Earth's surface that the height is comparable to, say, the radius of the Earth, then you can't use mg anymore. You actually have to use Newton's law of gravity. So there's one result we have, and that's something I'd given you earlier. There's another result too. We can calculate the work done in stretching a spring. So for instance, there's something called Hooke's law, which y'all have learned a little bit about. And Hooke's law says that when you apply a force F to an object, it's going to change its length by an amount delta x. And that delta x is directly proportional to the force, but the force is actually in the opposite direction. Meaning if I go from x equals 0 to x equals 3 centimeters, then delta x would be 3 centimeters minus 0, which is a positive direction, but the force will be in a negative direction because that's what springs do, or that's what metals do. And Hooke actually said this specifically about all objects. It's just in our labs, even if you took, say, let's say a piece of aluminum that was no bigger around than a pencil, but maybe was, 10 centimeters long. If you try to put enough force on that to compress it to move an amount, to basically compress enough that we could measure with a meter stick or something like that, you'd literally have to put almost tons on the actual aluminum. That becomes a dangerous situation. Things break, things fly, things could really harm you. So instead, we work with springs, which also obey the law, but they obey the law at much lower values of forces. So that's what Hooke's law is. And the negative, like I said, is just to indicate that the force that the spring applies is always restorative. So if I stretch the spring to the right away from equilibrium, it pulls to the left. If I compress the spring to the left past equilibrium, the spring pushes to the right. So that's what that negative is for. So what I'm going to do now is I'm going to imagine a mass on a spring, and the spring is going to be mounted to this wall. And again, I'm just using the spring specifically because that's what we use in our class. And I'm going to say this right here is the equilibrium position. So this is my y-axis. This is my x-axis. And I want to calculate the work I do in stretching it from x equals 0 to x equals x. So let's say, how much work do I do in stretching from x equals 0 to x equals x. Okay. Now, this is a frictionless surface. The mass is just there to show an object. We're not really doing any accelerating. We're trying to move it just as slowly as I did lifting the object a second ago. So I don't have to worry about accelerating that mass. So what I'm going to do is calculate solution work is equal to the integral of f dot dl. In this case, this is a variable force, so we actually have to do the integral. It's not too hard though. So I'm going to take the integral, and the force that I'm applying is actually going to have the positive sign because it's the force I'm applying. I pull it to the right, it goes to the right. So the force is going to be k times x in the I hat direction. And the dl is going to be in the x direction. So I'm going to call it dx I hat. And we'll say that since that's in the same direction I'm going, this indicates direction. Again, I'm just trying to be pedantic and say that you've got to make a thought about which direction you're going and which one of those two things is showing the direction and the other thing showing the positive coordinate direction. So I'm going to go from x equals 0 to just plain x, which every mathematician hates to see me do that, to integrate to dx to x, but I'm going to do it anyways because we can. Okay. So again, the linearness of this ends up making this integral of kx dx I hat dot I hat, which is 1. And that's going to be 1/2 k x squared from 0 to x, which equals 1/2 k x squared minus 1/2 k times 0 squared. So we've got a new potential energy function. This can be treated as if it's a potential energy. You could also count it as a work. It really doesn't matter. The main thing is you got to account for any energy stored in any springs. So U for a spring is equal to 1/2 k x squared, where this is distance from equilibrium. Okay, so we've got a new formula. We've got the potential energy of a spring. But again, like I said, you could call that work. You could call that energy loss because you're going to go into, cocking a spring or something crazy like that. All that's fair game. If you want to, there's another thing I want to do, the work energy theorem. I'll do that instead of, I will tell you that there's another potential energy, U, gravity. And your book derives this. I'm just going to tell you it's negative G times the mass of the object times the mass of the planet divided by the distance from the center of the planet to where you are. Okay, notice that negative, it's always there, and that's the only real negative that I use in my version of conservation of energy. Okay, so for instance, if I imagine taking off from a planet of radius r and mass m, and I'm going to try to fly out to infinity, okay? If this planet is so massive and its gravitational strength so high that I could only escape the planet by traveling at the speed of light, then my conservation of energy equation would become U initial plus kinetic energy initial plus work in is equal to U final plus kinetic energy final plus work out plus E loss. Okay, so in this case, what I'm going to do is I'm going to say the initial potential energy is G M M over R. The initial kinetic energy is 1/2 M C squared. Y'all haven't learned about kinetic energy yet, but you will. Okay, I'm not counting on any frictional losses or work or anything like that. So I get plus 0 equals 0 plus 0 plus 0 plus 0. In other words, when I'm infinitely far away, there should be no potential energy. I'm just barely making it out there with kinetic energy consistent with traveling at the speed of light, c. So it should come just to a stop as a bare minimum when I get out there. So the kinetic energy final should be 0. I'm ignoring air resistance and all that stuff. So work out is 0 and E loss is 0. So now what you can find out is that negative G M M over R plus 1/2 MC squared is equal to 0. If I choose to solve for R, this is going to make G M M over R is equal to 1/2 MC squared, reminding everybody that C is the speed of light. I'm going to get rid of this mass right here, and I will solve for R, and I'll get R. I'll tell you why I subscript it that way in a second, but I get R is equal to 2GM over C squared. Well, it turns out that is actually the Schwarzschild radius. And and it's relativistically correct, even though everything I did was not relativistically correct. The kinetic energy formula I used is not the correct kinetic energy formula for relativity. But lo and behold, if you do general relativity, you will find that the event horizon is at a distance r, which is given by 2 times g times m over c squared. And you guys, for extra credit, can determine r black hole for the Earth and r black hole for the sun. So in other words, if you look up the mass of the sun and look up the mass of the Earth, you can quickly do this calculation, turn it in, and I'll give you extra credit for that. Anybody have any questions about that? All right, I only got 2 minutes left, so let me quickly go through something. Let's start with Newton's laws of motion. So the summation of the force is equal to m times a. That's Newton's second law. Notice that left-hand side is the total work. So if I, or excuse me, is the total force. So if I wanted to calculate the total work done by something, then that has to be the total of all the forces acting on something. So I'd take the integral of the summation of all the forces dotted with dl, like that. Okay. Well, it turns out that I can also write the summation of the forces as m times a, and I can write the dl as dl, but I can also write the a as dv dt, and then I dot that with dl. Now, it turns out, and I've mentioned this a couple times in this class, those little d's that you see in the derivative, like dv and dt and all that, they're actually things that you can do mathematically. So it's not just a symbol. You can actually do this kind of stuff where you move the top part and take away the bottom part and that kind of stuff. So what I'm going to do is I'm going to change the order of dv and dl, and what I'm going to get is the integral of m dl dt dotted with dv. Can anybody, if maybe I told you instead of L, we use the vector R, could you tell me what dl dt is? Anybody? You might think about the units if you need help. Whoa. Anybody? All right, well, dl dt,
Velocity.
there you go, thank you. It's the integral of v dotted with dotted with dv. So that gives us 1/2 m v squared. And that's called the work energy theorem. And it basically says the total work done, no matter what, on any object is always equal to the change in kinetic energy. And K is defined to be 1/2 mv squared. So now you know that too has units of joules, but there's the formula for that. There's the formula for the work energy theorem. And in fact, if you're talking about that car, you'd say negative mu sub s m times g times d. That's the force, that's the total work done by friction. That's equal to final kinetic energy, which would be 0, minus the initial kinetic energy, which would be 1/2 m v initial squared. And you can see already that you can actually solve for the initial velocity, and that's what gets you a ticket or not in the event of a car wreck. Now that's it. We're done. I think I went over by a minute, but you guys are free to go. I'll wait for the last person to leave in case anybody has any questions, but you're free to go, and thank you for coming. We are finished with chapter 7. You're welcome.
I didn't see my exam that you told me I had to take.
You did not see it. Okay, let me check that then.
I see in Nessa or whatever for an exam?
Yeah, you know what? I think that's what happened. I think I forgot to change the name on it, and I just left it. And I meant to put the name on it for you, because it's actually a slightly different test. But I can get in here. Let's see. Thanks, Richard. Logan, did you have a question too, ma'am? I think that was, yeah, I think Logan's a female I talked to.
Yeah, can you unlock the chapter 6, 7, 8 practices?
Yes, I thought I'd already did that, but I definitely will. Oh yeah, see 6, 7, and 8. Yeah, thank you. I'll do that right after I finish with this.
Okay, thank you.
You're welcome. Let's see if this is right. I think this is, let's see, edit. See if your name's right on here. Yes, that's the one you're supposed to do. Richard. Oh, wait a second. Is your last name Joyner?
Yes.
Okay, scared me. I saw
Oh,
it.
it's different from up here.
Yeah, yeah, that's cool. Yeah, no problem. So you just take that one. It has the password that I told you about and everything. Actually, I don't even think I have a password on it because it only allows you to take it. Yeah, I don't have a password on it. So you should just be able to take that one. It looks like I've given you until tomorrow night at 11:59 p.m. Is that enough time for you, Richard?
Yeah, I was gonna take it right now. So
No, yeah, go for it. You got some time to take practice test too if you want, but good luck. Hope you do well.
all right, thank you.
You're welcome. See you, bud.